Hi, my name is James Walker, and I'm going to talk to you about my work with the experimental concept validation of touchless electric potential sensing using a pulsed electron beam. Spacecraft charging is caused by interactions between the charged plasma of the space environment and a spacecraft. As solar wind electrons and ions impact the surface of the object, they can stick, resulting in an accumulation of charge. During proximity and rendezvous operations, this leads to electrostatic forces between the two charged spacecraft. These additional forces perturb the relative motion of the spacecraft. Also, if the two objects have different potentials, arc discharges can occur during initial contact of docking operations. To account for this, techniques for remotely measuring a target's potential are being explored. These include the secondary electron and X-ray methods. Both employ high-energy electron beam to excite their respective particles from the target surface. For the secondary electron method, impacting electron beam electrons excite secondary electrons from the target surface and which are then accelerated towards the surfacing craft, where they are measured. The measured energy is equal to the difference between the surfacer and target potentials. Similarly, similar X-ray photons are emitted by the impacting electrons, which are subsequently measured by the surfacer. Their energy is equal to the difference between the electron beam energy and the target potential. Both these methods have been experimentally validated in vacuum chamber conditions. However, this electron beam applies an additional current to the target spacecraft that can significantly alter the measured potential. Because we want to measure the natural potential of the target, a method for reducing this current is being explored here. A pulse beam has been proposed for reducing the net current on an object. By pulsing, measurements are still conducted while the beam is emitting. However, the beam will also be off for periods of time, allowing the target to return to its natural equilibrium. By pulsing the beam, this should reduce the net current experienced by the object, scaled by the duty cycle of the beam, where the duty cycle is the ratio of pulse width to the total period of the pulse. The electron gun used in the experiments is capable of dual grid pulsing up to 5 kHz. Experiments are conducted in the Eclipse vacuum chamber, which has been specifically designed to study spacecraft charging. Connected outside the chamber is an exterior RC circuit that allows for us to simulate a space environment. Previous work demonstrated that the circuit accurately represented environmental currents experienced by a spacecraft. The spacecraft charging model is also used to compare experiments to a simulated spacecraft in the space environment. On the right is a picture of the experimental setup used throughout this paper, and on the left is an image of the exterior circuit. First, the secondary electron method was employed to ensure a pulse beam could be used to accurately measure a target's potential. You can see on the plot to the left, this steep drop-off in a measured current indicates the target potential. A cube with a negative 500-volt potential was used here, and you can see that both the continuous and pulse beam were able to accurately measure the target's potential. Next, floating experiments were conducted. Floating experiments refer to experiments conducted without the external the external circuit connected, so it is just the cube sitting in the vacuum chamber environment. The floating potential is the value where the flux of the incoming and outgoing electrons are equal. This value is determined by the electron beam energy, and so changing the current of the beam does not affect the potential. This means a pulse beam should generate the same potential as a continuous beam. The plot on the right shows that for a 5 keV and 6 keV beam, the top and the bottom respectively, the resulting floating potentials are the same. Next, we compared the charging behavior of a pulse beam to that of a continuous beam. These experiments are conducted by connecting the circuit and measuring the current through the resistor. The left shows the charging behavior of a 3 microamps pulse beam with a duty cycle of 0.5 and a continuous beam whose circuit has been scaled by the duty cycle, such that it is 1.5 microamps. It is shown that the charging behavior is very similar, especially for the first 60 seconds, where the beam is used to actually charge the object. Second 60 seconds, the beam is completely turned off and the system is allowed to discharge. This portion is similar but not perfect, which is likely due to the mechanical limitations of our electron gun. The image on the right shows a comparison between the continuous and pulse beams with a duty cycle of 0.01. Both beams have the same electron energies and current. The bottom plot is the same data as the top, but with a log scale, so you can see the pulse beam does in fact charge the object. you can see that the continuous beam charges the object significantly more than the pulse beam. In fact, 90% less. The pulse beam charges the cube more than 90% less than that of the continuous beam. You can also see that the pulse beam behavior doesn't seem to vary with energy. We explored this further and found that for this scenario, a pulse beam with a pulse beam up to 6 keV, we couldn't significantly charge the target object. Finally, we wanted to compare the charging behavior of continuous beam to that of the charging model. The plot on the right shows there is a clear distinction between the experimental data on the left and the simulated data on the right. This is likely due to unmodeled electron losses in the experimental setup. The charging model for the simulations, only a secondary electron and backscatter electron current are being simulated, while in the experimental setup, additional losses such as self-emittance are possible. Self-emittance means that for a charged object, some electrons can escape from the target surface. So the cube would still be losing electrons that are not modeled by the spacecraft charging model. In order to have a meaningful comparison between the experiments and the simulations, the total net losses of the experiments must be characterized and included in the charging model. From these experiments, we have shown two important concepts. For these experiments, the pulse beam acts similar to a continuous beam with a reduced current, and that a pulse beam can accurately measure a target potential with the secondary electron method without significantly perturbing the natural potential. We also discovered that simulations are not characteristic of our experiments, and we must perform more characterizations of the electron losses in our experiments. Thank you for your time.